classwork solutions for the concavity, day 4. Same as the last classwork. Alright, number 1, for the most part I believe I was able to check everybody's in class. So if you need to pause this slide to check your own work. Number 2, mod 1 I gave you x plus 2 cosine x. Mods 2 and 7 I gave you x plus cosine x. The first and therefore second derivatives are different, but the critical numbers, the number line, the intervals, and the points of inflection don't change. So this sort of got cut off, but f of 3 pi over 2 is also 3 pi over 2. But again, for the most part, I was able to check to your working class. Alright, number 3, I did the first and second derivatives. Now here, for those of you that I didn't get to talk to, you get a second derivative of negative sine minus cosine. So I saw that some of you factored out a negative 1. Then you get sine x plus cosine x equals 0. From here, some of you saw that the signs, meaning positive or negative of sine and cosine, would have to be opposite of each other to equal 0. So you knew that the critical numbers would be the second and fourth quadrant values of pi over 4, because in the second and fourth quadrants, the absolute value of the sine and cosine are the same. Just in the second quadrant, sine's positive, cosine's negative, and it's the opposite in the fourth. So you could have seen that. Going back to the original, if we add cosine of both sides and then divide again by cosine of x, you get negative tan x equals 1, and then dividing by negative 1, you get tan x equals negative 1. Now again, from here, what's your reference angle? Pi over 4. Because at pi over 4 the tangent is 1, and then in what two quadrants is the tangent negative? In the second and fourth. So 3 pi over 4 and 7 pi over 4 are our critical numbers. Okay, so I put those on a number line. Now a lot of us had discussion with testing values. So we're between 0 and 2 pi. So if 3 pi over 4 is your first critical number, then I would suggest plugging in pi over 2 into the second derivative. Plugging in pi over 2, you would get negative 1 minus 0, so that first interval is negative. Between 3 pi over 4 and 7 pi over 4, you could choose pi or 3 pi over 2. If we select pi, sine is 0, cosine of pi is negative 1, so the opposite of negative 1 makes that interval positive. And then I talked to a lot of you about what do I test between 7 pi over 4 and 2 pi. Please remember that the unit circle is symmetric to both the x and the y axis. So the first quadrant begins pi over 6, pi over 4, pi over 3. If we reflect this over the y axis, reference angle pi over 3, pi over 4, pi over 6 would be here. Now using symmetry over the x, 6, 4, 3 is our reference angle. Symmetry back over the y, 3, 4. So a test value in this interval would be 11 pi over 6. Cosine of 11 pi over 6 is square root of 3 over 2. Sine is negative 1/2. Plugging those values into the derivative, second derivative, excuse me, you would have negative square root of 3 over 2 plus 1/2. Negative root 3 over 2 is bigger than 1/2, so that would be negative in that interval. Concave down, 0 to 3 pi over 4, and 7 pi over 4 to 2 pi. Concave down, wrote it in the wrong interval. So our function would be concave up, between 3 pi over 4 and 7 pi over 4. Points of inflection would occur at the sign changes on the second derivative. Plugging 3 pi over 4 back into the original, we get the sine of 3 pi over 4 plus the cosine of 3 pi over 4. Sine of 3 pi over 4 is positive root 2 over 2. Cosine is its opposite, so the y value of the point of inflection would be 0, and same goes for 7 pi over 4. Sine of 7 pi over 4 would be the negative root 2 over 2, and because 7 pi over 4 is in the fourth quadrant, the cosine would be positive, but adding them together we get 0. Okay, number 4. I feel once we got the derivative, you guys were able to solve the problem. First derivative, I think for the most part, I saw the majority of you write the problem with a negative exponent. First derivative, bring the exponent down front, subtract 1 from the original exponent, and then multiply by the derivative of the inside. So negative 8x times x squared plus 1 to the negative 2. Now with this step, I directed most of you that I spoke to write the function with a positive exponent and use the quotient rule to divide. Some of you used product rule here and you got the answer correctly, but the product rule with a negative exponent is a lot less familiar than writing it in this form and using the quotient rule. So second derivative, bottom function times the derivative of the top function minus top function times the derivative of the bottom. So here we use power and chain again, all over bottom function squared. So it would be to the fourth power. Now we've looked at this often. All the terms have an x squared plus 1 in them. What can we factor out? The smallest exponent. So we can take 1 away from each term. Distributing the negative 8, negative 8x squared minus 8. Positive 8x times 2 times 2x would give us a positive 32x squared. And now combining like terms, 24x squared minus 8 all over x squared plus 1 quantity cubed. Once you got the second derivative set, I feel that the rest was okay. Setting the second derivative equal to 0, you got seemingly what looked like unfamiliar critical numbers, but once we put them on the number line, they were easy enough to evaluate. The second derivative always exists because if you attempted to set the denominator to 0, you would get x squared equals negative 1, which we know doesn't give us any critical numbers. So please review this. If you have any questions, make sure you see me. All right, now the tough one. And this one was tough algebraically. It was tough to find the critical numbers if you could even get to the second derivative. So rewriting the denominator as x to the 1/2 and applying the quotient rule. Bottom function times the derivative of the top minus top times the derivative of the bottom function all over bottom squared. Okay, a couple rules that I'll continue to come back to. Power to a power. We multiply like bases to combine. When you're multiplying like bases to combine those exponents, we add them together. All right, please, please, please don't forget all the work we did in the first chapter, okay? Simplifying complex fractions like this, so fraction within a fraction. Let me put this over 1. What's my common denominator of just the numerator? 2 root x. So first, before I can use a reciprocal, I'm going to get a common denominator. 2 root x times root x would give us 2x. Distributing the negative, right? Several of you had an issue there. Dividing by x is the same as multiplying by 1 over x. So I got a common denominator. I got rid of the fraction within a fraction. Now let's simplify. 2x minus x gives me x minus 1. 2 square root of x is x to the 1/2 power, plus 1 would give us x to the 3/2 power. Alright, so the second derivative would also need the quotient rule. Bottom function times the derivative of the top minus top function times the derivative of the bottom. So using the power rule, this is nice because it's not a negative exponent. 3/2 minus 1 would give us 1/2 all over bottom squared. So we have 2x to the 3/2 minus x minus 1. Now let's look at this. The 2's cancel, so I would have 3 root x on the outside all over 2 squared is 4. X power to a power I multiply. 3/2 times 2 would give me to the third power. So 2x to the 3/2. Now I'm going to distribute the 3 root x and the negative. So negative 3 root x times x would give me negative 3x to the 3/2 plus 3x to the 1/2 all over 4x cubed. These are like terms. Negative x to the 3/2 plus 3x to the 1/2 all divided by 4x cubed. So this is the most simplified second derivative. Well, maybe most simplified isn't the right term. You could factor out an x to the 1/2, but I'm going to work with this in that form. One thing that I spoke to several of you about, if I asked you for the second derivative, I would expect to see you simplify the x's more, but we need to manipulate the second derivative. So you can leave it in this form as long as you can get me another answer. Okay, so second derivative, negative x to the 3/2 plus 3 root x. Where does the second derivative not exist? We'll go back to the domain of the original function. Not only can x not be negative, it can't be 0 because of the square root in the denominator. So notice that cuts off our interval. Now I'm going to subtract the negative 3 root x from both sides and then square both sides. So again, power to a power, I multiply. X to the 3/2 squared would give me x cubed. Negative 3 squared is 9. Square root of x squared is x. Subtracting 9x from both sides. Factoring out an x. My critical numbers, just solving the equation, would be 0 plus or minus 3. 0 and negative 3, however, are not in the domain of the function. So now my test values 1 and 4 into the second derivative. Negative 1 plus 3 would give me a positive value. If I plug 4 in here, power over root, square root of 4 is 2. 2 cubed is 8. So I would have negative 8 plus 6. So that would give me a negative interval there. So function concave up from 0 to 3, concave down from 3 to infinity, and then a point of inflection. Plug 3 back into the original. It's not pretty, but it's an answer nonetheless. Please see me if you need any help on these. Like I said in class, focus specifically on numbers 1 through 4. Number 5 is a good challenge problem and something to practice multiple skills.